a tower designed to climb more than 1 kilometer into the sky, so tall that ordinary skyscraper engineering. If completed as planned, Jeddah Tower will soar over 1,000 meters, Located beside the Red Sea in western Saudi Arabia, this isn't just another skyscraper. It's the centerpiece of an entirely new urban district designed for the future. The project carries an estimated construction value measured in billions of dollars, combining luxury residences, but building higher than any structure before means confronting invisible forces that grow stronger with every additional meter. Wind quickly becomes the greatest enemy.
Did you see the look on his face when they mentioned the budget?
I know, right? He nearly dropped his coffee. Unlike conventional skyscrapers, every extra floor dramatically increases the weight pressing downward. Managing those forces becomes an engineering puzzle unlike any before. Solution. The HVAC routing in this quadrant needs optimization.
According to the analysis, that significantly impacts the budget.
We also have these architects imagined elegance, but structural engineers demanded stability. Every curve, angle, and dimension would ultimately be shaped by physics. The tower's distinctive three-winged form isn't just beautiful. It disrupts powerful wind vortices that could otherwise shake the building violently. Choosing where to build such a giant was equally critical. The wrong ground could threaten the entire project before construction even began. Before a single machine arrived, surveyors mapped every centimeter using GPS receivers, laser scanners, and aerial drones to establish perfect accuracy.
We're bringing up the core now. Looks like we have good recovery on this one. Secure it tightly.
Each soil sample was carefully analyzed for density, moisture, strength, and bearing capacity. The foundation would depend entirely on these results.
Meanwhile, environmental specialists studied groundwater levels, seasonal weather patterns, and the site's long-term stability decades into the future.
Meteorologists contributed another vital piece of the puzzle by recording wind speeds at multiple heights to predict conditions the finished tower would face. Thousands of measurements were combined into advanced computer simulations capable of predicting how the entire structure would behave long before construction started. Only after every survey, laboratory test, and simulation confirmed the site's potential could engineers finally approve construction. Now the real transformation begins. Before the world's tallest tower can rise, an enormous construction site minutes. With the site approved, attention shifted to the digital world, where thousands of engineers coordinated every bolt. Every discipline worked inside a shared building information model. If a ventilation duct collided with a structural beam, the conflict was solved digitally. Structural engineers then calculated millions of load combinations, from occupied floors to maintenance equipment, but gravity wasn't the only concern. At 1 kilometer high, the wind behaves very differently than it does at street level, demanding extensive physical testing. Hundreds of tiny pressure sensors measured how turbulent air wrapped around the tower, helping engineers refine its shape for maximum stability. Even subtle changes to corners, setbacks, and floor geometry could dramatically reduce wind-induced vibrations. Every contour served a structural purpose. Next came vertical transportation. Moving thousands of people through a 1 kilometer tower required elevators, unlike almost anything built before. Fire safety demanded another level of innovation. Protected refuge floors and pressurized escape routes were integrated throughout the tower's enormous height. Temporary utility networks delivered electricity, water, communications, and drainage long before permanent infrastructure would exist. Excavators removed thousands of cubic meters of earth, exposing deeper layers, while geotechnical engineers continuously verified ground conditions. Dust suppression became a full-time operation. Water trucks constantly sprayed haul roads to improve visibility and protect workers from airborne particles. Meanwhile, engineers installed temporary drainage systems to prevent unexpected groundwater or rainwater from flooding future foundation excavations. Every truck entering the site followed carefully planned logistics routes, preventing traffic delays that could disrupt thousands of daily construction activities. With the ground fully prepared, survey teams returned once again, marking the exact footprint where the world's tallest tower would finally begin. Now there was no turning back. Every measurement had to be nearly perfect, because even tiny errors at the base could multiply hundreds of meters above. The planning was complete. The desert was ready. Now comes the phase that will determine whether this giant can stand for generations: the foundation ends. Before the tower could rise into the clouds, engineers had to build downward first. The foundation would become the invisible structure. Instead of relying on a shallow footing, engineers selected a deep-piled foundation, capable of transferring enormous loads. Each pile location was marked with millimeter precision. A single misplaced foundation element could affect the alignment of the entire superstructure. Towering rotary drilling rigs then bored shafts several meters wide and extending dozens of meters into the ground through layers of sand and rock. As excavation progressed, drilling fluid stabilized the borehole walls, preventing collapse until permanent reinforcement could be installed. Every completed shaft was inspected using specialized instruments to verify its diameter, depth, and vertical alignment before construction continued. Next came enormous steel reinforcement cages, some stretching longer than a basketball court and weighing dozens of tons. Each cage contained thousands of precisely tied reinforcing bars, designed to resist tremendous compression, tension, and bending forces for decades. Lowering the cages required extraordinary precision. Even slight contact with the borehole walls could damage the carefully engineered reinforcement.
Concrete was then poured using tremie pipes, allowing fresh concrete to rise from the bottom upward while safely displacing the drilling fluid.
Every concrete delivery was continuously tested for temperature, consistency, and strength to guarantee uniform quality throughout the massive foundation. One by one, hundreds of foundation piles formed an underground forest of reinforced concrete, capable of supporting unimaginable weight. But individual piles alone couldn't support the skyscraper. They needed to work together beneath one enormous structural platform. Construction crews excavated around the completed piles, exposing their tops before trimming each one to its exact design elevation.
We need 2 more sections tied on the east side. Copy that, sending the team over now.
Waterproof membranes were carefully installed beneath the reinforcement, protecting the future structure from groundwater for generations. Engineers embedded thousands of sensors inside the reinforcement, allowing the foundation's temperature and long-term performance to be monitored after the concrete was poured. Beneath the desert. Beneath the desert, the invisible backbone of Jeddah Tower was finally taking shape. Next, engineers must build the conquerors. With the foundation complete, construction finally moved above ground. The first element to rise wasn't the exterior, This central core would house elevators, emergency stairs, and critical utilities, while resisting the enormous twisting. Thousands of tons of reinforcing steel were assembled with extraordinary precision, creating an intricate steel cage before each concrete pour. Instead of building traditional wooden forms from scratch, engineers relied on self-climbing formwork that lifted itself higher after every completed floor. Hydraulic cylinders pushed the massive steel forms upward with remarkable accuracy, reducing labor while accelerating construction high above the ground. Once the forms were locked into position, crews immediately began installing another layer of reinforcement for the next section of the core. High-strength concrete followed, carefully pumped upward through steel pipelines under tremendous pressure to reach the ever-increasing height. Each concrete batch was engineered to maintain workability during pumping, while achieving exceptional long-term strength after curing. As one floor hardened, the climbing forms advanced again. This repeating cycle allowed the tower to grow steadily toward the sky. Around the central core, crews constructed enormous perimeter columns designed to share the building's immense vertical loads.
Steel and concrete worked together as one system, combining the compressive strength of concrete with the tensile strength of reinforcing steel.
Watch the alignment on the far side. Okay, bring it down slowly. Clear the rebar. Keep it moving over there. Okay, bring in the hose back now. Watch the edge, it's getting high.
Tower cranes became the lifeline of the project, lifting reinforcement, formwork, machinery, and supplies hundreds of meters above the desert. These cranes were assembled section by section, growing taller alongside the skyscraper they were helping to construct. At higher elevations, even lifting a single load demanded constant monitoring of wind speed, weight, and crane balance.
Every lift followed a carefully rehearsed plan. One unexpected movement could endanger workers and delay construction across multiple floors.
Week after week, the skyline changed. The once empty construction site was transforming into the tallest structure humanity had ever attempted. But building the structure is only half the challenge. Next comes sealing a 1-kilometer tower against heat.
With the structural frame climbing skyward, another race begins. Thousands of custom-engineered facades.
Every glass panel is manufactured to precise dimensions. Even a few millimeters of error could disrupt the alignment of hundreds of floors above. Instead of ordinary windows, insulated glazing units reduce solar heat while maximizing natural daylight, critical in the intense Saudi climate.
Slow down, bring it left slightly. Okay, I'm securing the bottom clamp now. Looks good, lower it down.
Precision brackets anchor every panel to the structural frame, allowing the facade to expand and contract as temperatures fluctuate throughout the year. Weather-resistant seals are then applied to block rain, dust, and air infiltration while maintaining long-term flexibility. Behind the shimmering exterior, a diverse team of mechanical engineers, including African-American men and women and white men, and gigantic chilled water pipes are assembled first, forming the backbone of an advanced cooling system capable of serving hundreds of occupied floors. Next comes the electrical network. Thousands of kilometers of power cables are routed through dedicated shafts connecting every level of the tower.
Plumbing crews install high-pressure water systems, engineered to deliver reliable service across extraordinary vertical distances.
Fire protection follows close behind, with sprinkler networks, smoke control systems, and emergency water supplies integrated throughout the building. Now comes one of the tower's greatest engineering achievements: its high-speed elevator system designed to transport thousands of people every day.
Rather than one continuous journey, passengers transfer through strategically placed sky lobbies, dramatically improving efficiency inside the massive structure. Above the ceilings, ventilation ducts quietly distribute conditioned air, while advanced sensors continuously monitor temperature, humidity, and indoor air quality. Smart building technology connects lighting, security, energy management, and mechanical equipment into one intelligent digital control network. Before any area is approved, engineers inspect every installation using laser scanners capable of detecting even tiny construction deviations. Concrete samples, welds, bolts, and facade anchors undergo repeated testing to verify that every component meets strict engineering standards. Inspection drones now reach locations that once required dangerous manual access, capturing high-resolution images of the tower's exterior in minutes. The structure is nearly complete, but before the world sees the finished masterpiece, thousands of final details must come together. With construction drawing to a close, attention shifts from building the structure to perfecting every detail. The final phase is where stone flooring, premium wall panels, custom ceilings, and architectural lighting are installed floor by floor, transforming raw concrete.
Outside, landscape architects reshape the surrounding district with parks, plazas, walkways, and water features that connect the tower to the city below.
Roads, underground utilities, public transport links, and parking facilities are completed, preparing the development for thousands of daily visitors.
The pressure differential on the primary pump is fluctuating.
Ramping up the secondary loop now. Looks stable.
Elevators complete hundreds of trial runs, verifying acceleration, braking, door timing, and passenger safety before welcoming the public.
Emergency systems are tested next. Fire alarms sound, smoke control fans activate, and backup generators instantly take over during simulated power failures.
Engineers also monitor how the tower responds to wind, temperature changes, and normal occuworld.
Window cleaning systems quietly travel along the exterior, proving that even maintaining the world's tallest tower requires extraordinary engineering.
From the observation deck, visitors experience breathtaking views stretching across Jeddah, the Red Sea, and the expanding skyline below.
The observation deck is on the 80th floor.
Thank you.
We just moved into the residential area. It's wonderful.
If we adjust the support beams here, the load distribution improves significantly.
That aligns with the updated seismic requirements.
The tower is more than a record-breaking skyscraper. It represents decades of progress in structural engineering, materials science, and
Every pile beneath the ground, every reinforced wall, and every glass panel reminds us that whether it ultimately stands as the world's tallest building or inspires even greater achievements, its engineering humanity has always pushed beyond previous limits.
From bridges and tunnels to megacities and now tower interlace. The story of Jeddah the Tower proves that extraordinary engineering begins with